Hello student, today we will study collision and conservation of linear moment. Now let's start. So when you consider a system, okay, from basic concept you can consider system of more than two particles. Suppose there are four particles and you consider this a system, okay, and there are two particles and you consider this as a system. Okay, it's up to you that how many particles are there in your system, right? If external force acting on this system is zero, okay, external force acting on a system is zero, then linear momentum will be conserved. How you can see it? Just recall from Newton's second law. What is definition? Rate of change of linear momentum is equal to applied external unbalanced force, right? So from Newton's second law you can write external force acting on a system is equal to rate of change of linear momentum of a system, right, with respect to time. Now if external force 0, when you put this value 0, so differentiation of linear momentum is 0. That means linear momentum is a constant. Differentiation of constant quantity only with 0, right? So from there you can write that momentum of system must be constant. Okay, momentum of the system will not change. Okay, momentum of system will not change. What it mean? Okay, now you consider particles within system. If these particles are moving towards this and collide, okay, these particles moving towards this and collide. So whatever the force at the time of collision applied by this particle on this will be internal forces of the system, right? And internal forces will not be considered in this external forces. Okay. So for simplicity, here we will only consider the system of two objects or system of two particles. Okay. Now let's see the collision of two particles. Okay, and we will see their head-on collision and oblique collision. And more specifically, in this video, we will consider only head-on collision type problem. Okay. Now let's see. Okay. There are two objects m1 and m2 are having velocity u1 and u2 along the same line joining the center of masses. Okay, and they collide. What is collision condition? u1 must be greater than u2. It will collide. When u1 is greater than u2, then it will collide, and after collision it will have some velocity v1 and m2 will also have velocity v2. These velocity are along the same line, that is line joining both the center of masses, right? If this kind of situations are there, then this is called head-on collision. This type of collision is a head-on collision, right? And when velocities are along not the line joining center of masses, then those type of problem are under oblique collision. Okay, you can see this type of example. One object is moving in this direction and another object is moving in this direction. Okay, and after collision both will collide, and after collision this object is moving in this direction and that other object is moving in this direction. Now see, velocities before collision and after collision are not along the same line joining the center of mass. This type of collisions are under oblique collision. Okay, so here we have a velocity of approach and velocity of separation concept. Okay, for head-on collision we have defined, Newton has defined a term that is coefficient of restitution. Okay, so this is the term which define the what is the extent of collision. Okay, so here if you consider this u1 is greater than u2, with what velocity both the objects are approaching each other, this is called velocity of approach. This is called velocity of approach. This velocity of approach is u1 minus u2, and after collision this v2 is greater than v1. Okay, after collision this v2 is greater than v1. That means what is relative separation velocity? We call this velocity of separation. Velocity of separation here v2 minus v1. Okay, and for this collision we have defined the term coefficient of restitution, that is coefficient of restitution. Okay, denoted by E. This is nothing but velocity of separation divided by velocity of approach. This is velocity of separation, that is v2 minus v1 divided by velocity of approach u1 minus u2. Okay, so these are some terms we have defined. Now we will see what happened at the time of collision and why momentum at all the stages, that means before collision, at the time of collision, and after collision, why momentum is conserved, and what happens with kinetic energy of a system, whether it is constant throughout collision or it is decreasing, or what happens, we will see. Okay, now consider the situation. Here we have two objects moving with speed u1 and u2. Okay, this is u1 and u2, and after some time it comes in contact. Okay, this is the both the objects just come in contact. At this instant we will call this is a start of collision. Now see, condition for collision is only when both the bodies are in contact, that is only collision. Okay, so both the bodies are in contact, this is start of collision. So what happens, this object is like this object is like this, both objects are moving and it collide, right? When it collide, now see what happened, there will be deformation in body. Okay, there is collision, right? At the time of collision there will be deformation in body. Okay, so what happens after that deformation take place, that means there will be shape of shape change of the body. Okay, this is m1 and m2, again m1 m2, so deformations are taking place. So at the time of deformation both the center of mass, distance between center of mass is decreasing. Okay, now deformation is taking place. At some instant there will be maximum deformation. After that body will regain its shape and size. Okay, there will be maximum deformation, after that body will regain its shape and size. Okay, now see, deformation is taking place, there will be maximum deformation. Suppose this is for maximum deformation. Okay, so at the time of maximum deformation center of mass of both the body will be at a minimum separation, right? Because deformation is taking place, both the object is deforming. Okay, you can visualize it, right? So after maximum deformation what happens, both the object will try to separate. Okay, at the contact surfaces there will be forces. Okay, one object is applying force on other object. Okay, now there is a separation. Okay, at the time of separation this object, now it depend on body. Okay, it depend on body that whether this object can regain its shape or size or not. Suppose here I am considering this object get separated. Okay, this object gets separated with change in velocity v1, its velocity after collision is v1. Just after collision we are considering. Okay, both the objects are like this, but I am showing it separately here. Okay, just for clarity. So this is v2, v1 and v2, mass m1 m2. Now this is situation just after collision. Okay, and this one is start of collision. Okay, or you can say just before collision. So this is just before collision, just after collision. Till that both the bodies are in contact. This period we will call collision of both the object, right? So at the time of collision, what happens? You can see any situation. Suppose if you draw free body diagram of both the object, this is object M1 in deformed shape, M2. So on M1, force on M1 is acting due to 2. Both the objects are in contact. One object is applying force on another. The same magnitude of force but in opposite direction, F21 is acting, okay, on other body. Okay, so here Newton's third law is valid, right? So now see, if you consider system of one body, if you consider system of one body, let's say this is system. So on this system, there is a force on this body, there is a force acting in opposite direction of u1. Now see, u1 is in this direction, force is acting in this direction. So u1 will decrease, okay, u1 will change. After changing, what it become? v1, okay, this changing is due to this force. Similarly, on this object, velocity is u2, a force is acting in this direction, this u2 will change to v2, okay. So velocity got changed. But when you consider system of both the particles, so there is no external force acting on the system. If external forces are not acting on the system, what we can say? Momentum of the system will be conserved, okay, momentum of the system will be conserved when? At the time of collision also, okay. So what happens? Before collision, there is no force acting on the system. After collision of two particles, no force acting on the system. At the time of collision of two particles, no external force is acting on the system. So what we can say? Momentum before collision is equal to momentum at the time of collision is equal to momentum after collision, okay. So for momentum perspective, you can write momentum of a system before is equal to total momentum of the system after is equal to total momentum of the system at the time of collision, okay. So momentum is conserved throughout, right? So this is momentum. How you write momentum? Most of the time we write momentum, initial momentum is equal to final momentum, right? So now what about energy? Okay, what about kinetic energy? System total kinetic energy of this system is half m1 u1 square plus half m2 u2 square, okay. And before after collision, half m1 v1 square half m2 v2 square. Whether both will be same or there will be decrease in energy. Now let's see what happens when both the objects are colliding. There is a shape change. If there is a shape change, that means there are some energy utilized in deforming this body. From where this energy will come? Okay, this energy, you are not supplying any external energy. No external forces are acting on the system. So whatever the energy that is utilized in deforming this body must be from energy from system itself. That is kinetic energy of the system. Okay. So some portion of kinetic energy of the system is utilized to deforming the body, and that energy gets stored in the form of deformation potential energy. Okay. So what about kinetic energy? Kinetic energy before collision, now it is decreasing because some portion of kinetic energy is utilized in deforming the body. Okay. So kinetic energy is decreasing, right? So kinetic energy before collision is not equal to kinetic energy at the time of collision. Okay. Now you get the concept clear, right? Kinetic energy is decreasing and some deformation potential energy are there. Okay. Now after maximum deformation, body try to regain itself. Now it depends on a body, right? It depends on a body. If it is regaining its shape and size 100%, that is, whatever the kinetic energy had been utilized to deforming the body, that will be again converted to kinetic energy. right? Because there is no deformation, there is no deformation potential energy. So whatever the kinetic energy before collision was there, that kinetic energy will be equal to after collision. Okay, this type of collision is a perfectly elastic collision or elastic collision. Okay, if bodies are elastic, then the collision will be perfectly elastic, right? So at for that case, kinetic energy before collision is equal to kinetic energy after collision. Okay, now let's see briefly. Okay, now see, this is condition before collision, at the time of collision, and after collision. So this is if the body regains shape and size perfectly, that means there is a 100% gain of shape and size, right? That means there is no gain in potential energy or deformation energy, right? So total kinetic energy before is equal to total kinetic energy after. Okay, so what happened? Collision start just before collision. If you see total energy, so just before collision total energy was constant. At the time of collision kinetic energy decreases. Okay, this you don't know how it is decreasing, but it is decreasing, right? It is decreases to maximum deformation. After that it is again increasing and having some kinetic energy. This is before collision, this one after collision. At the time of collision kinetic energy decreases, right? At the time of maximum deformation there is a maximum decrease, right? This kind of energy you can visualize. Okay, so kinetic energy before is equal to kinetic energy after. Okay, and one more thing, momentums are conserved, right? Momentum before is equal to momentum after. So you have one equation here, you have another equation. Momentum before is momentum after. Just write those equations. Kinetic energy before half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Okay, and from conservation of momentum, total momentum before collision, that is m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Okay, when you solve both the equation you will get that v2 minus v1 divided by u1 minus u2 is equal to 1. Okay, when you solve both the equation you will get this relation. What is this? Remember it, this is nothing but coefficient of restitution. Okay, so for perfectly elastic collision, okay, either you say it elastic collision or perfectly elastic collision. For perfectly elastic collision E is equal to 1, coefficient of restitution is equal to 1. Okay, so whenever you have elastic collision or perfectly elastic collision, there is no loss of kinetic energy after and before. There is a decrease in kinetic energy at the time of collision. Okay, there is no loss of momentum before, after, and at the time of collision. Momentums are conserved. Okay, so how to solve it? You have to solve velocities after collision in most of the question v1 and v2. You required only two equations, but you have three equations here: kinetic energy equation, coefficient of restitution equation, and conservation of momentum equation. Okay, so avoid kinetic energy equation, just write two equation: conservation of momentum and coefficient of restitution. Okay, so for perfectly elastic collision, momentum conserve, coefficient of restitution 1, and energy conserve. Okay, now let's move to next type of collision. Now see, after collision, if there is some deformation in the body, that means whatever the kinetic energy has been utilized in deforming the body, it remains there. Okay, with some extent. So what you can say, kinetic energy, if you write total kinetic energy here, so before kinetic energy was like this, now it is decreasing at the time of collision, and after collision it can be like this. There is a slight gain in shape. Okay, so what you can write, slight regain of shape. Okay, slight regain of shape. This is not 100% safely gun, right? Not 100%. Okay. So there will be loss of kinetic energy. In this case, kinetic energy before is not equal to kinetic energy after. There will be some loss of kinetic energy. Okay. So in this case, you can't equate energy. You have to equate only conservation of momentum. That means m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. You required one more equation. One more equation, you have coefficient of restitution equation. That is v2 minus v1 divided by u1 minus u2. With this equation, you can solve any kind of problem. Okay. There will be some special case. So this kind of collision is known as inelastic collision. Okay. This kind of collision will be called inelastic collision. That means E is not equal to 1. Okay. E will be less than 1. Okay. E will be less than 1 or equal to 1. This will be inelastic collision, right? For this you can solve it. If E is 0, that means both the body collide and didn't get separated. Okay. For here, equal to side, no, this will be less than 1 only. Okay. E is less than 1, right? So by using both the equations, you can solve, right? In this case, energy will not conserve, but momentum will conserve, right? Now let's see a special case of inelastic collision. That means that is perfectly inelastic collision. Perfectly inelastic collision. Okay, now let's see. So if the collision is perfectly inelastic, that means whatever the deformation was there at the time of collision, whatever the maximum deformation was there, it will remains there, right? Both the body will move with common velocity after collision. It will not regain its shape slightly. Okay. So both the object will move together with common velocity. That is v1 is equal to v2 is equal to v. So what will be coefficient of restitution? 0. Okay. See, coefficient of restitution was v2 minus v1 divided by u1 minus u2. If both are equals, then it will be 0, right? So for this case, coefficient of restitution will be 0. So here, velocity of both the objects are same. That means both the object will move together. Will stick together and will move with common velocity. Again, there will be loss of kinetic energy, and this kinetic energy loss will be maximum. Okay, there will be maximum loss of kinetic energy. So for solving this common velocity, how to write? Just by conservation of momentum. That is m1 u1 plus m2 u2 is equal to, both objects are moving with common velocity. You can write m1 plus m2 into v. When you write v, that means you already have considered this equation, coefficient of restitution, right? Okay. So from here you can write velocity, final velocity is m1 u1 plus m2 u2 divided by m1 plus m2. Okay. You have velocity. If you are required to find loss of kinetic energy, okay, loss of kinetic energy, that is kinetic energy initial minus kinetic energy final. Okay, kinetic energy initial is half m1 u1 square plus half m2 u2 square. That is total energy before collision, right? And after collision, what is kinetic energy? Half m1 plus m2 v square. You have to subtract it, like half m1 plus m2 into v square. Now you have velocity from here. You can put this velocity. Okay, and after rearranging some part, you will get loss of kinetic energy. Loss of kinetic energy is equal to half m1 m2 divided by m1 plus m2 into this velocity of approach, right? u1 minus u2 square. Okay, this is laws of, or sometime you can also write relative velocity or velocity of approach. Okay, this is laws. This m1 m2 divided by m1 plus m2 is known as reduced mass of system, right? You can write it as a mu. This u1 minus u2 you can write it delta u. Okay, like this. Okay, so for perfectly inelastic collision, both the object will move with common velocity together. For that, E is equal to 0. For this loss of kinetic energy, half mu delta u square, where mu is reduced mass m1 m2 divided by m1 plus m2, and delta u, if both the object suppose moving with, this is moving with 5 meter per second, this one 3 meter per second, are in same direction. For this, delta u will be 5 minus 3, that is 2 meter per second. If both the objects are moving in opposite direction like this, so for this delta u, that is relative velocity of approach, right? Relative velocity of approach will be 5 plus 3, that means 8 meter per second. Okay, this is basically velocity of approach, or you can write it relative velocity, right? So delta u can be written like this: both the object in opposite direction, add it; in same direction, subtract it. Okay, so this is the case when both the particles was moving with different velocity. Okay, both the particles was moving with different velocity, and finally both were moving with common velocity. Then loss is like this. Okay, in higher studies, or if you are a class 12th student, then you will see that if you connect capacitor, two charge capacitor, one capacitor is at potential V1, another capacitor is potential V2. Okay, then after some time both the capacitor will have same potential, like same common velocity, right? For that, loss of energy will be like this. Okay, there you have to write reduced capacitance, that is C1 C2 divided by C1 plus C2, and this delta u is like this change of velocity. If you add positive terminal to positive terminal, then use potential like this. If you add positive terminal to negative terminal, use potential, change of potential like this. Okay, so in brief, and further you can also have this kind of problem: one disk is rotating, another disk is placed, what will be loss of kinetic energy? There will be also some kind of problem in loss of energy in the case of inductor. Okay, so for today this is sufficient, I think. Now just remember it briefly. What is coefficient of restitution for perfectly elastic collision? E is equal to 1, perfectly inelastic collision E is equal to 0, and for general inelastic problem E is less than 1. Okay, momentum is always conserved, kinetic energy is conserved only in perfectly elastic collision, right? Okay, thank you.